Good afternoon, everyone, and welcome to today's webinar on selecting the right filter for your application. Your microphone will stay muted throughout the presentation in order to avoid feedback. If you have questions, we will address them at the completion of the presentation using the Q&A feature of WebEx. You are welcome to type in the questions at any time. Our presenter today is Bart Morrick. Bart is an applications engineer at HBM with 27 years of experience in a variety of areas within our organization, including manufacturing, service, technical support, international support, sales, and application support of high-speed data acquisition systems and sensors. Bart, it's all yours.
Thanks, Krista. So today's presentation will be discussing choosing the right filter for data acquisition. Filters can be found in almost every electronic circuit. They are used in audio systems for preamplification, equalization, and tone control. In communications, filters are used for tuning in specific frequencies and eliminating others. This webinar will discuss the use of filters and issues with different types that one should consider when making measurements with data acquisition equipment. The user needs to pick their filter based on the application they wish to record. Typically, we offer two different types of front-end analog filters, Bessel or Butterworth, and then also offer a wideband, the absence of any filter. There is no such thing as a perfect filter, and so you, the user, needs to weigh the pros and cons of each type in order to make an educated decision on which you're going to use. The Bessel and Butterworth filter differ in their frequency and step response, so your measurement priorities will determine which method you choose. Then we'll discuss analog versus digital filters. The next consideration we will investigate is the use of analog filters as opposed to digital filters. When an analog filter is implemented, it is done before the analog to digital conversion, whereas a digital filter is done after the analog to digital conversion. Then lastly, we're going to consider some of the techniques one should use when using a filter of any mode when recording and analyzing your data for post-processing. We hope that you find today's presentation useful, and we thank you for attending today's webinar. One of the simplest examples of a filter that we will see is the input of your measuring instrument. In this particular case, we offer an input with a DC, AC, or ground coupled input. In the DC mode, the filter is designed to pass all signals input into the channel. The entire portion of the signal will be passed directly to the amplifier. For example, if you're looking at a small ripple on top of a control signal, you'll need to consider the 100 millivolt of signal riding on top of the 5 volt TTL level. This means that your amplifier range has to be set to a minimum of 5.1 volts in order to look at the 100 millivolt signal that you're really interested in. This means that you're only using about 2% of your amplifier range. In the case of a 16-bit digitizer, you would only be using approximately 10 or 11 bits of resolution. In the AC coupled example on the right, all the DC portions of the signal are now blocked or filtered out. The only signal that then passes is the 100 millivolt signal of interest, allowing us a much closer look at that signal than it was not possible in the DC coupled measurement made earlier. HBM offers a wide range of data acquisition systems that differ in capabilities. We offer systems that are lab-based and offer multiple small, rugged, multi-channel systems. Feel free to take a look at our site at www.hbm.com and then click on the link for data acquisition systems for more information on the specific instruments we offer. For the purposes of today's seminar, I'm going to focus on our GENDAQ system and how the filtering works inside of it. Here's a basic circuit. An analog signal is sent into a signal amplifier. In the analog in section, we would have the gain and signal conditioning, which executes the functions such as conversions from current to a voltage signal, voltage excitation for connected sensors, amplitude gain, and voltage level shifts. From there, the first stage is offered where optional analog, low-pass, or anti-aliasing filters are offered and selected by the user. This can be used to reduce out-of-band frequencies that can degrade the analog to digital conversion. Then the signal is digitized in the second stage. This digital conversion from The ADC transmits a digital representation of the gain filtered analog signal to a digital processor. In the third stage, secondary digital filters are applied to the signal, and then finally it's stored. A filter determines the amount of attenuation that the amplifier provides and at what frequency that attenuation begins at. In an analog filter, each resistor-capacitor pair provides an increase in the order number of the circuit. You will hear terms like fourth order or seventh order filters when discussing different types of filters. This is where this comes from. In a digital filter, the digital filter replaces the hardware filter with an algorithm that simulates what the analog filter does. Because of a lack of component space, most amplifiers will have a 3 or 4 order filter. Our larger lab instruments may have up to a 7-order filter. The ideal filter will allow frequencies in the passband between 0 Hz and the cutoff frequency to be passed and not attenuated at all. As soon as you reach the desired frequency, the filter blocks off all higher frequency components. All frequencies above the cutoff frequency will be totally removed from your data. However, reality shows us that the attenuation already starts in the passband range, and that frequencies higher than the cutoff frequency are attenuated but are still transmitted into the signal. The definition of the cutoff frequency is the reduction of the amplitude between 10 and 30%, but this is approximately -1 to -3 dB down. And then, since there is no such thing as a perfect filter, you must decide which mode works best for you. In the example provided here, the Bessel filter on the left is shown with its roll-off characteristics, considering a first, third, or 10th order filter. On the right, the Butterworth filter shows the effect of the same orders of filters. If you look carefully, you'll see that the shape of the response is different because of the number of orders of the type of filters used. In the Bessel filter on the left, you can see the rate of decay increase or get sharper as the number of orders increases. The roll-off at the peak on the Y scale does not change drastically before the 3 dB down point, but it does change as the frequency increases in the X scale. In the Butterworth filter on the right, you'll also see that the rate of frequency decay, but you'll also see that the roll-off as the filter reaches the bandwidth frequency flattens as the order number goes up before it starts its sharp decay. So looking more in detail at the Bessel filter, we're going to examine the amplitude and frequency characteristics of the Bessel. As we discussed earlier, the signal in a Bessel filter will not be linear as you approach the cutoff frequency. It starts to decay. However, looking at the response curve on the bottom for the Bessel filter, we can see that there is a minimum overshoot. The phase delay is very linear and the group delay is flat in the passband region. This allows the Bessel to be a good choice when making transient measurements, as the shape of the waveform will be very well represented, such as in a case as in mechanical or ballistic applications where waveform shapes are a top concern. Here we can see the characteristics of the Butterworth type filter. We can see that the signal accuracy or amplitude is very flat all the way up to the cutoff frequency and has a very steep roll-off once that value is met. This will allow you to measure the amplitude of signals with very good accuracy. However, the step response diagram shows the drawbacks. You'll see that there's an overshoot and nonlinear delays in the passband. So you do not want to use this filter when making transient measurements, but this should be considered when making sinusoidal measurements for such applications as performing FFTs, vibration analysis, shock response, and harmonic measurements. All right, so why do we want to use filters? On some of our data acquisition systems, 2 different basic filters are used. There's an anti-aliasing filter. These are filters that are in front of the A to D, and signal filters. These could be analog filters and in front of the A to D, or these are digital filters after the A to D. Anti-aliasing filters, why do we use them? Anti-aliasing filters prevent signals that are greater than half the system sample rate from being recorded or undersampled. Undersampling leads to spurious display of non-existent signals called aliasing. Filters that prevent this are called anti-aliasing filters. They have a corner frequency that is less than half the sample rate of the data acquisition system, and if the corner frequency is set with the sample rate, they are called automatic anti-aliasing filters. When making a recording of data, you're taking an analog signal and converting it into a digital one. What happens is the system asks the digitizers to make a series of measurements, and based on the frequency of the signal, you need to make enough measurements to accurately represent that incoming signal. In this example, we are making 10 separate measurements for one cycle of a sine wave. When we join the individual measurements together, the yellow trace, we get a relatively accurate representation of the sine wave being measured. Nyquist's theory states that you need to sample at least 2 times the rate of the highest frequency that you are interested in if you want to make an accurate measurement. However, 2 times, while it may give you an accurate frequency component, it will not give you an accurate representation of the signal form and amplitude. If you take a look at this signal, you only see 2 points on the cycle, and since the sine wave, and by connecting the samples in a straight line, you'll not get an accurate representation of that sine wave. Continuing with our previous example, we see that by undersampling, the yellow trace is a completely inaccurate representation of what the original signal is. We had our data acquisition system make only 6 measurements over the 6 cycles of the input signal. The end result is a classic aliasing effect, a sine wave of the wrong frequency being displayed. We input a 25 Hz signal, but we are seeing a stored result of only 2.3 Hz. Again, what happened is we have a totally different signal frequency shown, the alias frequency. There are a couple of things that you can do. You can oversample your data or have an anti-aliasing filter. Oversampling would mean having your data acquisition system sample at a rate of 10 to 20 times the highest frequency component that you're interested in. This will allow you to see a better representation of the data actually measured. The GENDAQ system has the selection of a front-end analog filter that is followed by an optional secondary digital filter that has a value which is based on the sample rate of the channel that acts as the automatic anti-aliasing filter. Alright, so why signal filters? Signal filters are used typically to suppress unwanted frequencies. They help eliminate noise. They can prevent false triggers on spurious events not of interest. Some examples would be to suppress high-frequency noise injected into lead wires. And then there's trial and error. Because often you don't know what the trouble frequencies are, and the ability to choose from a variety of filters is useful. But you want to use care and not to disturb your original signal too much. The next few slides are going to show you a basic example from filtering and its needs. The screenshot that I've included here is a simple 350 ohm quarter bridge strain gauge mounted on a bending beam. I made a simple recording with no bending involved. So you're going to see an excess of noise riding on my signal. This noise is 60 Hz from a reading lamp with a fluorescent bulb that is placed on my desk, and other high frequency noise in the air near my unshielded, highly sensitive strain gauge sensor and amplifier. The amplifier is set for a wideband recording of half a second. I then exercise the beam, and you can continue to see the 60 Hz signal riding on top of my bending motion. Next, I'm going to make a simple recording after enabling the amplifier filter setting to show both the flat trace and the result of exercising the beam again. Here you can see a significant drop in the frequency noise and the 60 Hz noise from my lamp in close proximity to my sensor. Exercising my beam, you can see how significantly cleaner this signal appears with the use of a front-end filter. There are other techniques that one can use to improve on signal integrity, such as shielding, object orientation, etc., that could reduce some of the 60 Hz and other high-frequency noise without filtering away effects that are actually there and of interest. One of our past webinars, Measurement Cables and Shielding, can be viewed on demand from our website for additional details regarding some of these recommendations. Side effects of filters. While useful, filters do have drawbacks. There is a possibility of amplitude errors near the cutoff frequency that we discussed with Bessel filters. Non-matching filters will also introduce the possibility of phase shifts in channels, and this can be a real issue if you're dealing with structural issues. Time alignment is key, and even a small mismatch can cause issues in properly analyzing your data. Imagine if you're doing a large-scale structural test and have dozens of channels, and the data doesn't correlate properly. The impulse response of the filter may not give you an accurate result. An undershoot or overshoot can give you erroneous results if, for example, you need to calculate the area under a curve for some sort of energy calculation. There are pros and cons for every type of filter, and it is important that you consider each when making your selection. Is going wideband always the safest selection? Not necessarily, as we discussed earlier, as the noise in the circuit may swamp the amplifier. The key thing to remember is that your positives should outweigh your negatives when making a filter choice, and if all possible, all filter settings should match, or at least you should be aware of how they are different. Every electrical circuit has an embedded filter in it. All of our inputs have an input impedance, such as 1 megaohm or 40 picofarad, and you may be using a times 10 or a times 100 probe to cut down on the voltage signal being sent directly into the input. As I mentioned earlier, the ideal filter will allow a signal up to a certain frequency to pass and then blocks all frequencies above this. A real filter does not have that sharp a transition. So a 3 dB point, or the frequency cutoff point, this is the point in the channel's frequency response that begins a rather increased attenuation instead of passing the signal through. This is seen as the half power area, since a fall of 3 dB corresponds to half power, a voltage ratio which is the square root of 1/2, which is 0.707. So up to a certain frequency, the signal passes with less than minus 3 dB attenuation. After this frequency, the filter attenuates the signal more than the minus 3 dB. How fast this attenuation is the filter slope, and is based on the design stacked RC combinations. A higher order filter is a better filter because it is sharper, but it is more expensive. And for a point of reference, a first order filter offers additional 6 dB of attenuation for each doubling of the frequency. Each filter that you have will delay the signal. This delay in the signal is called a phase shift. The phase shift is a function of your input frequency. One way to avoid this is to have all the channels use the same manner of filtering and sample rate. Now, if you do have different filter settings, you are introducing the possibility that you'll see some phase mismatches. It is important that you minimize any phase shift, especially when doing any sort of enhanced frequency analysis on your data. The next few slides will give you an idea of some of the possible effects of phase shift on your data. We'll be looking at the same signal teed off to two different channels. We will compare the two signals with the same filter settings and with different filter settings. And we're going to also look at repetitive signals and transient events. In this example, I'm entering a 33 Hz sine wave into two channels into my HBM data acquisition system. Both channels are set up identically. Please note that the filter type in both channels is set to wideband, and then wideband is defined as an absence of a filter. Capturing a short recording, I'm able to analyze the recording and find that there may be an approximate 2 microsecond shift in the sine wave, channel to channel, which converts to a phase shift of about 25 milledegrees. And as a note, any delay here is probably due to the manner in which I teed the signal off. In this particular instance, I daisy chained the signals instead of having a common junction point. This method then introduces another slight delay because of the additional cable length that channel 2 sees that channel 1 does not see. Okay, and so for the next recording, I used all of the same channel settings except that I changed the filter type in my channel 2 to a Bessel filter. And again, make a short recording to compare the two channels. To the naked eye, in the top portion of the display, it appears that the two channels overlap each other cleanly. Zooming in, though, you'll see that there is a separation between the two traces due to the filtering differences. The red trace is my channel that has the Bessel filter enabled on it, and you can clearly see the delay between the two channels. Looking at the delay here, I now see that there is a 110 microsecond delay, which becomes a 1.3 degree phase shift in the same signal. It is clear that you want to make certain that your settings match across channels, or that you are at least aware of the differences in order to be able to explain any issues that may arise, such as thermocouple signal sampled at a slower rate versus a strain channel sampled at a higher rate. Now again, I'm looking at the same signal on two channels, and this is a transient signal with the filter settings matched. The channels overlap each other very nicely and closely. Now I change my settings back to have different filter settings between my two channels, and then create a new transient signal. Here, without even zooming in, you can clearly see the delay in the filtered channel 2, the red channel, when looking at the transient signal. Impulse response, overshoot, pre-shoot. So the effects appear around a fast transition, a square wave, or a transient signal. This is also called the impulse response. It's critical to minimize overshoot when doing any sort of time domain analysis. As a side note, pre-shoot is only there when doing a digital filter, not on the analog front-end filter. So there are different types of filters that are available to you, analog and digital, and we'll discuss some of those here. Analog, Bessel. Now, a Bessel filter is usually used for time domain analysis. It has high signal fidelity for transients and statistical inputs. It has excellent impulse response, almost no overshoot, but the phase shift is significant. It's good for time domain signals, but it's bad for frequency domain signals. Analog Butterworth. Now this is usually used for frequency domain analysis. It has great slope and phase match, but there's lots of overshoot and pre-shoot to transient or single shot events if too close to the sample rate. So it's good for frequency domain, bad for time domain. The analog wideband is really the absence of a filter. The limiting factor for bandwidth is caused by the input resistance capacitance of the amplifier. Wideband means that there are no extra filters. It provides the best signal fidelity and phase match, but there's no aliasing protection and noise reduction. Not every one of our amplifiers from HBM offers a wideband setting. The digital filters, we have digital IIR. So now this is a mathematical method for digital filtering. The acronym IIR stands for Infinite Impulse Response. So this emulates different analog filters, including a Bessel style filter. FIR, again, is a mathematical method for filtering. The acronym stands for Finite Impulse Response, and that emulates more of a Butterworth style filter. It's important to know that digital software filters alone cannot prevent aliasing. The filters on the digital are applied after the A to D conversion. So if aliasing occurs before the conversion, digital filters cannot prevent aliasing or remove spurious signals caused by the aliasing. Digital filters applied online are introducing a phase shift. So if a digital filter is used, offline phase shift might be prevented, depending on the filter that's used. All right, as I mentioned earlier, I'm going to focus on the GENDAQ approach to filters. So the GENDAQ offers a selection of filters. The user is allowed to make a selection based on need, filter type or frequency selection. The input boards offer flexibility to achieve the proper filtering We have analog filters, digital filters, and then digital data decimation. So in our first stage, we make a selection of anti-aliasing filters. We can choose Bessel or Butterworth, bypass or wideband. This uses a selectable filter best suited for your current measurement task. In the second stage, we have a low noise, high speed flash A to D or a sigma delta A to D. And that's always running at the highest sample rate. A fixed ratio, less than 0.5, between the A to D sample rate and the fixed analog filter to prevent aliasing is available. In the third stage, we make our selection of digital filters. So the IIF or the FIR are none. And that enables us to do noise reduction. The filters here are synced to the decimation that we'll discuss in stage 4, and the combination gives us an automatic anti-aliasing filter. Digital decimation on stage 4 is the full speed data to the desired sample rate. So together with the digital filter in front of it, stage 3, aliasing is prevented. Several ratios between the digital filter sample rate and the sample decimation rate enable the best choice reduction with the least signal distortion. Okay, what does that mean to the user? So the GENDAQ offers a selectable filter characteristics, Bessel, Butterworth, wideband. There's fixed frequency filters, so there's no switching. Digital filters and decimation are located later in the stages. Because the filters are fixed, they can be done as high-order filters. High-order filters give the best aliasing in addition to high bandwidth. And then switchable analog filters and high orders are very expensive. So it's another thing to keep in mind. The automatic anti-aliasing filters, the filter frequency is switchable and gives the best fit for every application. Selecting a ratio between the filter frequency and the sample rate allows the filters to be used as a noise reduction filter. So how do you use these within Perception, the controlling software for the GENDAQ? So you go to the Perception setting page and you set your analog input filter. And then from there you're able to choose a digital anti-aliasing or noise filter. Each channel can be set independently. If a Bessel or FIR filter is selected, the desired frequency is selected. This frequency is a ratio between the filter type selected and the sample rate selected. So for the FIR filter, you can set the frequencies to 1/4 of the sample rate, 1/10, 1/20, 1/40. The IIR filter can be set to frequencies of 1/10, 1/20, 1/40, 100. If you select wideband, no other filter selection is needed or available. So the spreadsheet just shows you the different filter choices with our basic DC amplifier set to 1 megasample per second and 100 kilosamples per second sample rate. So you can see the type of filters and selected in each mode. So if we have the IIR filter, the FIR, it tells you we've got a 220 kilohertz 7-pole Bessel or a 370 kilohertz 7-pole Bessel, and then the frequencies that are available to them. The last thing that we're going to discuss is some post-process or post-acquisition digital filtering. The post-process digital filtering is available for additional filtering. Now these include IIR filters, again stands for infinite impulse response. This emulates different analog filters including Bessel, Butterworth, or Chebyshev style filters. Some of the filters that are available to you post-process are low pass, high pass, a band pass, or band stop. Now it's important to know that, again, digital filters alone cannot prevent aliasing. Filters apply to a signal after the A to D conversion and storage. If aliasing has already occurred during the conversion, digital filters cannot prevent or remove the aliasing. It's also need to remember that if filters are performed on multiple channels, the same filter should be used if time alignment is necessary. So the post-process Bessel filter, again, has many of the same characteristics of the filter types whether they're analog, digital, or post-process. So again, Bessel has good linear phase response, good step response with little overshoot. The frequency response is worse than Butterworth, but it should be used when the phase relations are critical. It's best used in the time domain when using signals that contain non-sinusoidal signals like square waves and noise or transients. It's the best choice of all the different frequency components of the original sine wave. Will have almost the same delay after they've been filtered. A positive, it has the best step response with very little overshoot or ringing. On the negative side, it has a slower initial rate of attenuation beyond the bandpass than Butterworth filters. The Butterworth digital filter, signal processing filter designed to have a flat frequency response, a good frequency response with no ripple. The phase response may be non-linear on high-order filters. It's best used in the frequency domain. A sinusoidal signal is best filtered with a Butterworth. Non-linear issues is not bad because we would typically be dealing with one dominant frequency. So on the positive side, we have a flat magnitude response in the flat band. We have good all-around performance. The pulse response is better than a Chebyshev filter, and the rate of attenuation is better than a Bessel filter. However, the negative, there's some overshoot and ringing in the step response. The Chebyshev filter has a steeper roll-off and more passband ripple than Butterworth. It minimizes the error between the idealized and actual filter characteristics. Compared to Butterworth, the Chebyshev achieves a sharper transition between the passband and the stop band, but it's best used in the frequency domain. It has a better rate of attenuation than the Butterworth, but there's ripple in the passband, and it has considerably more ringing in the step response than the Butterworth. So we're going to look at a couple of pages of plots quickly on some of the digital filters and how they react. So we have the magnitude spectrum, and then the magnitude in the stop band. So the Bessel has, you can see that the Bessel, the red trace, has the worst frequency response in the stop band. The Chebyshev, the violet trace, has the steepest roll-off, but has ripple in the passband. All right, and then looking at the magnitude spectrum of these three filters, we see that the Bessel, the red trace, has the worst frequency response in the stop band, and that the Chebyshev has the steepest roll-off, but has ripple in the passband. Then looking at the impulse response of the three filters, the Bessel filter provides the best impulse response of the three filters. You see that the higher red trace and the impulse as opposed to the Butterworth and the Chebyshev. Now some of our filter options also offer the capability of performing phaseless filtering. So phaseless filtering is performed by reverse order technique. The signal is filtered twice after it's been captured. Order of the used filter is half of the entered value. So step number one, the signal is filtered as normal, and then step number two, the signal is filtered again, but the points go through in a reverse order. So again, how it works, the filter is used twice. The overall filter is equal to the entered ordered value. An odd value for the order will be the first even value below the off value. For example, an entered value is 7, then the filter will have an order value of 6. The phase shift then will be 0. The magnitude spectrum and the phaseless and non-phaseless mode is shown here. The phaseless filter is a result of filtering with a filter with half the order size twice. Now on the magnitude spectrum, we see that the phaseless filter, we could show the phaseless and non-phaseless. The phaseless filter is a result, again, of filtering with a filter with half the order 2 times. And then the attenuation of the cutoff frequency is 6 dB down and not 3 dB. Going back to our earlier measurement, we can look at some of the bending beam and see how the post-acquisition digital filtering will look when a filter is applied. If you remember, this is our original signal, wideband, and no input filter settings selected. Now, after performing a filter on the same data, you'll see the bottom trace is the result of that filter. The original signal is still there. We just created a second trace that filters out the high frequency noise and 60 hertz from the fluorescent lights that were interfering with our signal. So, this concludes our presentation. Remember that when using an analog filter, it is done before the analog to digital conversion, whereas a digital filter is done after the analog to digital conversion. Analog filtering can remove noise that rides on the signal before it reaches the analog to digital converter. This can eliminate extraneous noise peaks. Analog filtering is more suitable for high-speed systems, say greater than 5 or 10 kilohertz. A concern to be aware of is the possibility of anti-aliasing, so the sampling speed of the digitizer has to be considered. Digital filtering cannot eliminate noise peaks riding on the original signal like an analog filter can. A digital filter uses oversampling and averaging techniques to reduce noise. Since the digital filtering occurs after the analog to digital converter, it can be far more programmable than an analog filter can, which allows the user the capability of programming the cutoff frequency. Lastly, we considered some of the techniques possible in using a filter of any mode when post-process analyzing your data. There are many things to consider when making a measurement, and the number one consideration that I would recommend is to make certain that if you are using filters during your acquisition, that you make certain all channels are set to the same settings to avoid any phase shift mismatches. We hope that you found this presentation useful, and we thank you for attending today's webinar.